All right, in terms of looking at the direction of flow in a shell and tube heat exchanger, the first thing we're going to look at is a parallel flow heat exchanger. Now, in a parallel flow, the flow from both the fluids is going in the same direction. So they are both entering here on the left side, and they're flowing in the same direction, and heat is being transferred along the length of the tubes, and then they both exit at the other end. This results in a temperature profile like this, and I'm going to show this temperature profile here. And this is temperature here, and this is the temperature in of the hot fluid, and then this is the temperature in of the cold fluid, and they're both entering at the same side here on the far left. And this right here, oh, I messed that up. Let me get this right here, 100%. This is the tube length. Tube length. So initially, the inlet is really hot, right up here. Should have made that in red, my bad. The inlet is really hot, and the inlet of the cold is really cold. But what happens is, as they flow along the length of the tubes, is the cold gets hotter, and the hot gets cooler as they flow. And then this is the outlet right here. This is where the water, both fluids, hot and the cold, exit the heat exchanger. This is the outlet. So you can see a characteristic of this heat exchanger is they start with a very large difference in temperature at the inlet of the heat exchanger, and the entire length of the tube bundle, that differential temperature is coming down. All right? If you'll turn the page, or at the bottom right, you'll say, you know what, we could take that same exact heat exchanger and we could just reverse the directions of flow, and we get what's known as a counterflow heat exchanger. That changes everything. What that means is we're going to enter and flow opposite one another. So you're looking at your picture. One fluid's going to come in here and flow that direction. The other fluid could come in and flow that direction. They're flowing in opposite directions versus parallel flow where they're both going in the same direction. Well, that's going to change the temperature profile. And you'll see T in, and it results in this. And there's the possibility that this right here, this temperature of the hot, as it's exiting here, it could actually, at the end of the heat exchanger, be cooler than the exiting temperature of the cold. This means it's really efficient at transferring heat. And this, once again, is the length of the tube bundles from 0 to 100% tube length. So they don't start out with that big a difference in delta T, and it really, really goes away. This is a unbelievably efficient heat exchanger, and it is the only one. Parallel flow cannot cross temperatures like this. So one of our knowledge requirements, it says right there, hey, we need to know the flow paths for heat exchangers, both counterflow, cross-flow, U-tube, all right? And here's a note, cross-flow heat exchangers are super, super efficient. Finally, we're going to look at, this is cross-flow. Counterflow are really efficient as well. But cross-flow are pretty good too, and let's look at them. Now, typically when we talk cross-flow, let's see the difference. Parallel flow, I'm just going to use arrows. Parallel flow, the two flows were going in the same direction. Counterflow that we just looked at, the flows in the heat exchangers were going in opposite directions in the heat exchanger. And we found out that this was actually more efficient. And then the last thing we look at is cross-flow. Cross-flow is one flow is like this and one flow is like that. And now this would be similar to our condenser. And what happens is if we look at that profile, let's look at that profile. what occurs in the condenser is the temperature in the shell side of a condenser is based upon the operating pressure of the condenser, and it's a constant. So this is the temperature in the shell. This is temperature. And then I'm putting a cold water in, or a cold fluid, and it's then, and there's a difference in temperature right there, and then it is then going along the tube bundles and increasing its temperature. So this is the tube length once again right here, tube length. And you can see that this temperature is slowly rising. So if this was a cross-flow heat exchanger, like a condenser, I could have this going on right here, where steam is being deposited in the shell, and it's going to have a constant temperature until it gets down into here, the hot well, drops in here to the hot well, and then the tubes, and I'm just going to make these tubes go the length, oops, so then the cooling water would come in, and it slowly, as it travels the length of the tubes, it's going to pick up energy, and that's what this is doing. You can see the temperature is going up of this circulating water, right? So a constant temperature in the shell side, an inlet temperature that's cold, an outlet temperature that's hot. What's key here is, think about your rules that I gave for our heat transfer equations. In the shell side, there is a phase change. So I can't use that one equation, if you'll recall. Mass flow rate times C sub P times T hot minus T cold. I can't use that equation to determine how much energy was transferred from the steam to the circ water. However, the circ water is going from cold to hot, and it's not boiling. It's going from, say, 60 degrees to 80 degrees on the outlet. It didn't have a phase change. So I could say something like this. Well, all of the heat transferred out of the steam is equal to all of the energy that's transferred into the water. So then I could say, well, there's a phase change. I could say mass flow rate of the steam times change in enthalpy of the steam is equal to mass flow rate of the water times C sub P of the water times T hot minus T cold of the water. And this is what we're going to get into and have to really understand these rules, so that these questions just become second nature.